So now it's time to turn our attention to the final subclass of task gang that shows off yet another Java synchronizer for barrier synchronization. And this is called CyclicSearchWithPhaser. And this is by far the most complicated implementation because it's super cool. And what it does is it showcases the Java phaser barrier synchronizer. And as you can see by looking at this particular UML diagram of the public methods in phaser, it's got about 4 times more methods than countdown latch and maybe 3 times more methods or more than CyclicBarrier. So it's got a lot of cool stuff going on here. I'm just going to recap some of the key features of the phaser. You can take a look at the asynchronous videos if you want to know more. It's very, very, very cool, but we don't have time to cover it all right here. So it allows a variable number of thread objects to wait for all operations and other thread objects to complete their word searches. So this is more flexible than CyclicBarrier or countdown latch, which can only support a fixed number of parties or threads. And a good human known use of this would be different work crews with different numbers of workers coordinating their tasks when, say, building a house. So you might have one work crew who comes in with 3 people to do the framing. You might have another work crew with 2 people to do the electrical wiring. You might have a work crew with 5 workers to do the roofing or the bricking or whatever, but each work crew could have a different number of workers. This particular Java barrier synchronizer is well suited for variable sized cyclic entry and or exit barriers. So it supports all these 3 capabilities. The number of parties can vary dynamically as the program runs. Now, you can also use this for fixed size use cases, but quite frankly, it's overkill. Phaser is way too powerful to be used if you just have a fixed number of parties. If you have a fixed number of parties, you probably just want to use the good old CyclicBarrier. So let's talk about the CyclicSearchWithPhaser implementation, which uses a phaser to search for a variable number of words using a variable number of thread objects concurrently until there's no more input to process. The key theme here is variable number. Previously, we had a fixed number. Now we have a variable number. And what we're going to do is we're going to have each thread run the same logic, just like it's always done before. However, the number of worker thread objects and array elements may differ on each cycle. Now, the number of worker threads and array elements will always be the same, but they can differ from cycle to cycle. So if you start out with 4 and then the next cycle has 3, you've got to get rid of one of the threads and you've got to reduce the count of the phaser by 1. We're going to make a phaser to wait for all thread objects to finish each cycle, and we'll also need to update the phaser on each cycle using the onAdvance hook method shown here whenever a reconfiguration is required if the number of threads change between the cycle. The reconfiguration process is going to be complicated, and it's going to use a CyclicBarrier to manage reconfiguration. And I'm not going to show it here. We'll talk about it when we look at code. The CyclicBarrier that we use coordinates the reconfiguration of the gang of tasks, which really are threads, and those things may grow or shrink each time through. And we'll talk about how that works when we look at the code in more detail. The task done method is also much more complicated. What it's going to do is it's going to call a method on the phaser called arrive and await advance. And when that gets called, that's going to wait for all the threads at that point to wait to all get there. And then we're going to check to see whether or not a reconfiguration has occurred. Reconfiguration occurs if the next cycle has a larger or smaller number of threads. And if there's a larger or smaller number of threads, then that's going to cause a reconfiguration to take place. And we're going to use the CyclicBarrier to do that. If we end up with fewer threads in the next cycle, then we're going to deliberately call the index out of bounds exception, which will cause the thread that catches it to shut itself down voluntarily because it knows it doesn't have anything else to do because it's not needed for the next cycle. And we use an exit barrier to wait for all the thread objects to finish. This is the same as before. We use countdown to alert the main thread when there's no more input left to be processed. And the main thread will call await, which will block until all the cycles have finished. So let's go ahead and take a look at the code to do this. So here we are in CyclicSearchWithPhaser. And as I mentioned before, this is by far the most complicated variant, and that's because it has a variable number of strings that it processes. If we look at the options singleton, you can see the variable number of strings. So we have 1 followed by 5, followed by 2 twice, followed by 1, followed by 3. So we've got lots of different types of strings, and that's going to end up generating different numbers of input elements and different numbers of virtual threads. We handle this by making ourselves a phaser, and we also have a reconfiguration Boolean and a reconfig CyclicBarrier that's used to coordinate or synchronize all the threads when reconfiguration is triggered. The constructor is easy. It just calls up to the super class as usual, passing in the words to find and the strings to search. We start out by not requiring reconfiguration, and then we go ahead and make our phaser. Now notice the phaser is only made once, but it's then updated and modified multiple times based on the runtime behavior as the number of threads and parties vary. So to make this thing, we have a factory method called makePhaser, which will will make a new phaser and it will override its onAdvanced method. So you can see here the onAdvanced method takes in phase and the number of registered parties. And what we're going to do is every time this gets called, we're going to figure out the current number of input elements, and then we're going to get the new list of input strings to process. If there in fact are no strings, we're done. We bail out. That causes the thing to start shutting down. Otherwise, we figure out what the new size of the new list of input strings are. Remember, again, as we saw before, you could have different numbers each time through. So we're going to figure out whether we need to do a reconfiguration. We need to do a reconfiguration if there's a difference between the new size and the previous size. If there's not a need for a reconfiguration, we can just start another cycle, pick up from where we left off. Everything's hunky-dory. If there is, however, a need for a reconfiguration, we print that to the output to indicate a reconfiguration is taking place. And then we go ahead and make ourselves a cyclic barrier that will manage this reconfiguration, passing in the previous size, which is the number of threads we had before, and the new size, which is the number of threads we're going to have now. So let's go ahead and take a look at make cyclic barrier. What make cyclic barrier does is it makes a new cyclic barrier, which will have the previous number of threads. We have to wait for that many threads that we're currently running to finish. And then we give it a barrier action. This is what's going to get run after that many threads reach this barrier. And what we do is we check to see if previous size is less than the new size. In that case, we have to go ahead and create new tasks / virtual threads in order to be able to run these new elements. So we call it get executor, execute, make task on the number between the prev size and the new size. And then we also indicate that a reconfiguration has finished. So we are no longer going to need to do any more reconfigurations at this point. So that's what make cyclic barrier does. So we get that cyclic barrier back, it gets set up here. And we're going to see how that gets used here in momentarily. Okay, so that is what we do for making ourselves a phaser. Now let's go ahead down here and take a look at make task. So what make task does, make task has been customized from what you get out of the box with the search task gang common. And what it's going to do is it's going to go ahead and register this thread with the phaser we created. So it knows it's included in the set of registered parties. And then we call up to the superclasses make task in order to actually make the runnable. So this is what we just did before. This is the one that we get from here, which is from search task gang common. So that's the same as before. The difference is that we register ourselves first dynamically. Here's the initiate hook. It just prints out some diagnostics. Here's task done. Task done is quite a bit more interesting and tricky. You can see we'll potentially throw the index out of bounds exception. So we come in here and we make ourselves an index out of bounds exception that we set to null initially. And then down here, we're going to call arrive and await advance. This is a phaser operation that's used to wait for all the other tasks that have registered as parties. And remember, we registered as parties up here in the make task method, waits for all of them to reach this barrier point. And when they all have arrived and they're all awaiting advance, then they all advance together. Now, when they advance, the next thing they do is they check to see if a reconfiguration has occurred. If a reconfiguration has occurred, then we have to wait for all the existing threads to reach this point. So that's what prev size was. If there were 4 threads before and there are going to be, let's say, maybe 3 threads this next time, we have to wait for all 4 threads to reach this point. And then we're going to go ahead and check to see if we still need the current thread. If our thread is greater than the new size of the input list, in other words, if the input list shrank relative to before, we arrive and deregister, which says we're no longer needed here. And then we make ourselves a new index out of bounds exception at this index. And you can see what happens if the exception is non-null. We throw that exception, and that will end up getting caught deep in the bowels of the framework, and it will clean up that thread because that thread was no longer needed. So as you can see here, this is very, very subtle code. It's super duper cool code, but it's very subtle code, not as obvious as what's going on. And you'll also notice that we used the volatile keyword for this M reconfiguration Boolean. And that's because we need to make sure that we can atomically check it down here to see whether or not we have to trigger a reconfiguration. And these could be getting called in different threads. So remember, by making this field atomic, that means that it'll be atomically read from and or written to. And so you always know you get the latest, greatest version. Okay, so that's a bit of a complicated implementation, but it really does a nice job of showing off some of the cool features of phasers to work with variable numbers of inputs, variable numbers of threads, and it shows how we can use CyclicBarrier to manage the reconfiguration of these things.